Hello everybody. Very good evening students. Welcome to 3-day marathon for AP GENCO, TRANSCO and DISCOMs. And the subject we are going to discuss now, it is the power systems. So myself, DMV Prasad, the faculty member of ACE Engineering Academy. Now we are going to discuss some important questions and expected questions in the coming examination for AW students. So I'll start with the first question. A short transmission line having its line impedance angle as 30 degrees. For getting 0 volt regulation, the receiving end power factor angle should be. That is the first question. A short transmission line having its line impedance angle as 30 degrees. So what is the line impedance angle, students? The line impedance angle is given. Line impedance angle is given as theta, actually it is 30 degrees. And they're asking for 0 voltage regulation. What is the condition for 0 voltage regulation? What is the condition for 0 voltage regulation? The condition for 0 voltage regulation. What is that one? The power factor angle plus the impedance angle must be equivalent to 90 degrees. Where the power factor angle is 90 degrees minus theta. Where 90 minus theta, it is 90 minus 30. 90 minus 30. It will be 60 degrees. So where phi is the load power factor angle. The load power factor angle should be 60 degrees. 60 degrees. Right, students? Phi plus theta is equivalent to 90 is the condition for 0 voltage regulation. What is the condition for maximum voltage regulation? Condition for maximum voltage regulation, just can recall here. Condition for maximum voltage regulation, the power factor angle is equivalent to the line impedance angle. Right. This is the condition for maximum voltage regulation. Condition for maximum voltage regulation. Right. So we'll see one more question here. The next question. A 10 kilometers transmission line is operating at a frequency of 1000 hertz. The transmission line is electrically short transmission line, electrically long transmission line, any of the above, both A and B. So it is given that the line length is 10 kilometers and the frequency of operation is 1000 hertz. When frequency of the system increases, the charging current flow in the line is also increasing. So whenever charging current flow increases, you cannot model the line as a lumped model. We have to go for the switching transient model. Switching transient model. The switching transient model we are having is the long transmission line. The long transmission line. It is one of the easiest question we can say. And one more question, students. So it is also one of the easiest question related to the string efficiency. A string insulator has 5 units. The voltage across the bottommost unit is 35%. Its string efficiency is. So what is the percentage string efficiency formula? What is the percentage string efficiency formula? Percentage string efficiency is equivalent to total voltage across the string divided by n is the number of disks and Vn is the nth disk, that is the bottommost disk voltage, where the total voltage across the string is not given and number of disks are 5 and voltage across the bottommost disk is 35% of the total voltage. It is 0.35 times that of the total voltage into 100. Right. So V total will be cancelled. If you calculate this one, 1 by 5 into 0.35. 5 into 0.35. It will be 57.14%. 57.14% the answer. That is the voltage across the bottommost disk. The next question is a system of 66 kilovolts. The line to ground capacitance is 0.02 microfarads and inductance is 4 Henry. When the magnetizing current of 8 amperes, find the voltage appearing across the pole of a circuit breaker. Anybody, please try to solve the problem. The system is of 66 kilovolts. The line to ground capacitance is given 0.02 microfarad and inductance of the transmission line is given 4 Henry and the magnetizing current is given 8 amperes. Find the voltage across the circuit breaker contacts. What is the voltage across the circuit breaker contacts? The voltage across the circuit breaker contacts is I root of L by C. I root of L by C. Where I is 8 amperes, under root of L is given 4 Henry divided by C 0.02 into 10 power minus 6. So if you calculate this one, 8 root of 4 divided by 0.02 into 10 power minus 6. It is 113.13 kilovolts. 113.13 kilovolts. That's option A is the correct answer. Again, one of the easiest question related to the circuit breaker, that is power system protection. The next question, a zero sequence network of a three-phase transformer as shown in the figure below, the corresponding transformer connection will be. So it is given that the zero sequence network of a transformer connection is given, right? They're asking what type of connection is this one? What type of connection is this one? Is it star ground, star ground, star unground, star solidly grounded on both sides, delta on both sides, delta star grounded, delta star grounded. If you see, we are having a transformer. For a transformer, there are two switches in series and two switches in shunt. So this is a series switch. This is also series switch. These two can be operated or closed for star connection, that is star grounded connection. These two can be closed for a delta connection, right? So when primary is delta, the series switch will be opened and the shunt switch will be closed. Suppose if secondary is also delta, secondary series switch is opened, shunt switch will be closed. This is the circuit diagram they have given, right? So this is delta, this is also delta. Therefore, the transformer connection is delta connection. delta connection. Right. So directly by seeing the shunt switch connection, we can give the answer. Very simple question. Right. A 132 kilovolts three-phase system circuit breaker has natural frequency of 20 kilohertz during fault. Calculate the time taken to reach the peak value of restriking voltage. So what is the time at which restriking voltage is peak or maximum? They are asking what is the time for maximum value of restriking voltage. Restriking voltage. The restriking voltage will be maximum when omega t is equivalent to pi. What is the restriking voltage equation, students? The restriking voltage equation is the active recovery voltage into 1 minus cos omega n into t. Whenever omega n into t is pi, 1 minus of minus 1, it will become 2, so that it will become maximum. 2 times of AR is the maximum. Therefore, so restriking voltage is maximum. VRES is maximum at omega n into t is pi, where t is pi by omega n, which is nothing but pi by omega is nothing but 2 pi into f. 2 pi into f. Where the frequency is given 20 kilohertz, substitute that one, it will be pi divided by 2 pi into 20 into 10 power 3. 20 into 10 power 3. So substitute those values, students. It will be pi divided by 2 pi. Pi will be cancelled here. Pi will be cancelled. 20 into 10 power minus 3. It is 25 seconds. But 25 seconds is not given. So we can write as 0.025 milliseconds. 0.025 milliseconds. Right. Sorry, it is 10 power 3, right? So directly we got this one. How much you got? Direct answer is 0.02. It is kilo. It is 0.025 milliseconds. Right, perfect. The next question. In a short circuit test on a 66 kilovolts three-phase system, the breaker gave the following results. Power factor is 0.5. Recovery voltage is 0.9 of full line voltage. Calculate the active recovery voltage. Calculate the active recovery voltage. What is the active recovery voltage formula? The active recovery voltage is nothing but some constant K1, K2, Vm sin phi. So in the question, K1 it is given as 0.9. There is no information about K2. We can take it as K2 as 1. So we can take as the fault as the grounded fault. And the value of Vm is nothing but root 2 times of V phase RMS. Where it is root 2 times of V phase is nothing but 66 divided by root 3. That is the phase voltage. That is the RMS phase voltage. That is V phase. And cos phi is given 0.5. As a result, phi is equivalent to 60 degrees. And we have to take sin phi. which is root 3 by 2. Sin 60 is root 3. Substitute these values, students. Substitute these values. Therefore, the active recovery voltage is equivalent to some constant K1 is 0.9, K2 is 1, Vm, it is root 2 into 66 into 10 power 3 divided by root 3 into sin pi, it is root 3 by 2. So we can give the answer in kilovolts so that we can remove this 10 power 3. So the answer is in kilovolts. The answer is in kilovolts. This will be 0.9 into root 2 into 66 divided by root 3 into root 3 by 2. Root 3 by 2. So we are getting 42 kilovolts. 42 kilovolts as the answer. Right. Right, students? It is also one of the easiest question related to the circuit breakers again. Right, students, one more question. If the percentage reactance of the system up to the fault point is 40% and base MVA is 25, then short circuit MVA. What is the short circuit MVA? If the percentage reactance of the system up to the fault point is 40% and base MVA is 25, then the short circuit KVA, the short circuit KVA is. So actually, MVA given, what is the value of MVA given? It is 25. 25 MVA. 25 MVA. That is the MVA base value. Or it is 25 into 10 power 3 kV. 25 into 10 power 3 kV. They are asking KVA SC. KVA SC. Right. MVA SC in terms of KVA. What is MVA SC, students? It is MVA base divided by Z per unit. The per unit impedance is given 0.4. It is 25 into 10 power 3 kVA divided by 0.4. How much is 25 divided by 0.4? It is 62.5. 62.5 into 10 power 3. 62500 kVA. It is 62500 kVA. 62500 kVA. That is the short circuit KVA in terms of KVA, students. Not in terms of MVA. See the units clearly. Right. Next question, students. A three-phase 20 MVA 11 kilovolts alternator has internal reactance of 6% and negligible resistance. Calculate the external percentage reactance per phase to be connected in series with the alternator so that the steady state short circuit current on short circuit does not exceed 10 times that of the full load current. 10 times that of the full load current. It is given that the short circuit current is 10 times that of the full load current, that is the base current. That is the base current. When you are multiplying ISC with V base into ISC into 10 power 6 is equivalent to 10 into I base into V base into 10 power 6. This is MVA base. This is MVA-SC. Therefore, MVA-SC is 10 times of MVA base. MVA base. That's what the statement given. That's what the statement given. Right. MVA base is given 20 MVA. Right. Therefore, MVA-SC is nothing but 10 into MVA base is how much it is? 20. It is 200 MVA. And we know that MVA-SC is nothing but MVA base divided by Z per unit. Then which is nothing but 200 MVA. Right? Or otherwise directly you can calculate here itself. You can substitute, not required these steps. Here you can write it is MVA base divided by Z per unit is equivalent to 10 into MVA base. MVA base will be cancelled. Z per unit is 1 by 10. That's sufficient. This calculation is not required. This calculation is unnecessary. Therefore, what about Z per unit is equivalent to 1 by 10? It is 0.1 per unit. 0.1 per unit. It's already given the internal reactance is 6%. Right? So, 0.1 means you can write it as 10%. Na? It is 10%. But existed reactants. Now, what is the existed reactants we are having? 6%. Therefore, extra reactants required. How much it is? 4%. So 4% is the extra reactants required. See the question? So we have taken ISC is 10 times that of the full load current. That is the base current. That is the rated current. And we have multiplied on both sides with V base into 10 power 6, V base into 10 power 6. We have cancelled MVA base and MVA base. And we have calculated Z per unit. Right, students? See the next question. A 3-phase induction motor is connected to a supply of 400 volts 50 H. Its power factor is 0.6 lag. So initial power factor is 0.6 lag. A delta connected capacitor bank is connected across it to improve the power factor to 0.8 lag. So second power factor is 0.8. The rating of induction machine is 4.5 kVA. The value of capacitance per phase will be dash microfarad. So how much is the capacitance required in microfarad to improve the power factor? It's also a very simple question. Right. We know the initial power factor cos phi 1 is given 0.6. As a result, what is the value of tan phi 1, students? If you calculate this one, cos inverse of 0.6, we'll get it as 53.13. Tan of that one will be 1.33. Cos phi 2 is given 0.8. Cos inverse of 0.8 is 36.86. Tan phi 2 is 0.75. 0.75. Now, the reactive power supplied by the capacitor QCSH is nothing but the active power demand of the load into tan phi 1 minus tan phi. Where the active power demand of the load is nothing but apparent power is given S and the power factor is given load power factor 0.6. It is S demand into cos phi. It is 4.5 into 0.6 kilowatts. 4.5 into 0.6. It is 2.7 kilowatts. That is active power demand. Now calculate QCSH, students. The value of QCSH is nothing but 2.7 into what is the formula? Q into tan phi, P into tan phi 1 minus tan phi. So tan phi 1 is 1.33 minus 0.7. So it is 2.7 into 1.33 minus 0.75. That will be 1.566 kVAR. But we need per phase value, QCSH per phase. Why? Because we have to calculate per phase capacitance. QCSH per phase value is 1.566 divided by 3. Divided by 3. 0.522 kVAR. 0.522 kVAR. We know that QCSH per phase value is nothing but, or otherwise directly you can write the capacitance formula. What is the capacitance formula? Capacitance per phase is nothing but QCSH per phase value divided by omega into V phase. It is 0.522 kVAR into 10 power 3 divided by omega is 2 pi into 50 into 2 pi into 50 into V phase square. What is the value of V phase, students? The delta connected capacitor bank. Across delta, the total line voltage is coming as the phase voltage 400 volts. So it is 400 volts. Right? So calculate this one. It is 0.522 into 10 power 3 divided by 2 pi into 50 into 400 square. It is 10.38. 10.38, approximately 10.4 microfarad. 10.38 microfarads. It is 10.4 microfarads. Right. Alright, students. So you have to remember the formula. So this is one of the most important formula. Right? And this is also the most important formula to calculate QCSH. QCSH. So voltage control is very, very important topic, students. And power factor correction. Right. Next question. So it is from generation. What will be the reserve capacity of a power plant having maximum demand of 100 megawatt? Given plant capacity factor is 0.45 and utilization factor is 80%. They are asking reserve capacity. Plant capacity factor is given 0.45. Utilization factor is given 80% and maximum demand is given 100 megawatt. What is utilization factor? Utilization factor is equivalent to maximum demand divided by installed capacity. Installed capacity. So it is 0.8 is equivalent to 100 divided by installed capacity. Therefore, installed capacity is 100 divided by 0.8. What is 100 divided by 0.8, students? 100 divided by 0.8, it is approximately 125. 125 megawatts. Then, what is reserve capacity? reserve capacity is installed capacity minus max only. It is 125 minus 100, it will be 25 megawatts. So here there is no need of plant capacity factor. There is no need of plant capacity factor. Next question, students, from economic load dispatch. The operating costs of two generating units operating at economic load dispatch are C1 is 10 P1 plus 8 into 10 power minus 3 P1 square rupees per hour. C2 given 8 P2 plus 9 into 10 power minus 3 P2 square rupees per hour, where P1 and P2 are in megawatt. The total operating cost to supply a total load of 100 megawatt. Total load. The total power demand is nothing but P1 plus P2. They have to supply. How much it is? 1000 megawatt. Let it be equation number 1. And the incremental fuel cost of plant 1. What is the incremental fuel cost of plant 1? It is differentiation of C1 divided by dP1, which is nothing but 10 plus 16 into 10 power minus 3 P1. What is IC2, students? It is DC2 divided by dP2. DC2 divided by dP2. It is 8 plus 18 into 10 power minus 3 P2. For economic operation, incremental fuel cost of plant 1 must be equivalent to incremental fuel cost of plant. For economic operation, incremental fuel cost of plant 1 must be equivalent to incremental fuel cost of plant. What is the incremental fuel cost of plant 1? We got it as 10 plus 16 into 10 power minus 3 P1 is equivalent to 8 plus 18 into 10 power minus 3. This will be 0.016 P1 minus 0.018 P2 is equivalent to 8 minus 10 will be minus. This is equation number. From equations 1 and 2. Solve for 1 and 2, students. Solve equations 1 and 2. So we are having P1 plus P2 is equal to 1000. And one more equation is there. 0.016 minus 0.018 is equivalent to minus. We are getting the value of P1 as 470.588 megawatt, and the value of P2 is equivalent to 529.411 megawatt. The other two equations we got. Two values, P1 and P2. And they're asking what is the total cost, total operating cost to supply. Total operating cost is nothing but C1 plus C2. Total cost is F total is nothing but C1 plus C2. Therefore, F total is nothing but, what is the value of C1, students? C1 is nothing but 10 P1 plus 8 into 10 power minus 3 P1 square. Substitute the value of P1. What is P1? 470.588. 470.588. It is 10 into 470.588 plus plus 8 into 10 power minus 3, 470.588 whole square plus. Second one is 8P2. 8 into P2, it is 529.499 plus 9 into 10 power minus 3, it is 529.4. Substitute these values, friends. Substitute these values. It is 10 into 470.588 plus 8 into 10 power minus 3 into 470.588 square plus 8 into 529.411 plus 9 into 10 power minus 3 into 529.411 square. It is 13235.27 rupees per hour. So 13235. 13235. 13235. Option A is the perfect answer. Somewhat lengthy question. Sometimes expected. Right, students? One more question. So in the faults, a three-phase synchronous generator with 1 per unit terminal voltage supplying 50% of total power it is able to deliver initially. The receiving end voltage is also maintained at 1 per unit. The equivalent reactance between sending end and receiving end before the fault, during the fault, and after the fault are x1, x2 and x3 are given respectively. The maximum possible load angle if a three-phase symmetrical fault at the middle of the reactance is right. So here we are having a generator which is connected to an infinite bus. The generator voltage is 1 per unit and infinite bus voltage is also 1 per unit. Both. So that E is given 1 per unit, V is also given 1. It is generally delivering 50% of the total power it is able to deliver initially. Right? So P1 is 0.5 times of PS1. 0.5 times of PS1. And the equivalent reactance between sending end and receiving end before fault, x1 equivalent is given. We know that P max 1 is nothing but E into V divided by x1 equivalent. E is given 1, V is also given 1, x1 equivalent. x1 equivalent is given, it is 1 per unit. So where P max 1 is 1 per unit. P max 1 is 1 per unit. You can write here. The initial power, the initial power is P1.5 PS1, where the initial load angle delta naught is nothing but sine inverse of PS by PM1. PS by PM. PM1 means P max 1. P max. And the delta max, maximum delta value is 180 minus sine inverse of PS by P max 3 PS by P max 3 where P max 3 is nothing but E into V divided by X3 equivalent. X3 equivalent. Where E is 1, V is also 1. X3 equivalent is given. How much it is given? X3 equivalent is 1.7. It is 1 by 1.7. 0.57. That is the P max 3 value. You can calculate PS value. If you got PS value, you got the answer, right? You got the answer, right? So initially, suppose if you are taking PS1 is 0.5 times of P max 1. P max 1 we got. P max 1 initially it is able to deliver. Out of that one we are delivering only 50%. So that how much is now P max 1? P max PS. PS is nothing but 0.5 times of P max 1. 1. That is 0.5. Therefore, what is the value of delta max, students? Delta max is nothing but 180 minus sine inverse of PS is 0.5 divided by 0.57. How much is this one? 180 minus sine inverse of 0.5 divided by 0.57. So approximately you are getting 120 degrees. 120.221. 120.221 degrees, right? So try to understand the statement here. So it is given that initially it is delivering 50% of the total power. Total power means it is the maximum power. So initially it is delivering PS1, which is nothing but PE1. Actually, initially we have to take electrical power is exactly equivalent to mechanical input. You should not take PE1 is nothing but 0.5 times of PS1. That's wrong. Initially, PE1 and PS1 both are same before the disturbance. After the disturbance, the electrical power will change. Right. Like that you can tell. So one of the direct question, nuclear binding energy in the energy is the energy equivalent to in the nuclear power plants, nuclear binding energy is nothing but mass defect. Mass defect. Right? In comparison to conventional steam power plant, geothermal power plants have lower load factor, same load factor, higher load factor, and any of the above. Right? The geothermal power plants compared to that of steam power plants are always having the high value of the load factor. High value of the load factor. Compared to that of the steam power plant, right? They are having high value of the load factor. And they are more economical also compared to that of the steam power plants. Right. So next question, students. In electric field, the electric field intensity on the surface of the aluminum conductor compared to that of the surface of the copper conductor will be dash to have same resistance. They are comparing aluminum conductor and the copper conductor both. The electric field intensity on the surface of aluminum conductor is always less than that of electric field intensity on the surface of the copper conductor. As a result, corona on the surface of aluminum conductor is always less than that of corona on the surface of the copper. That's why aluminum conductor is always preferred. It's always less. It's always less. Yeah, one more question. The potential across the string insulator can be made equal by capacitance grading method, in which C is the shunt capacitance. Right, students? So shunt capacitance value is given C. And C1, C2 and so on Cn are the self capacitances of the discs from top to bottom continuous. If the capacitance of the topmost disc is 10C, so means C1 is 10C. Then the capacitance of the fifth disc. So according to capacitance grading, Cn plus 1 is equivalent to Cn minus 1 plus Nc. Cn minus 1 plus Nc. C means CSH. What is that? C2 is nothing but C1 plus CSH. C1 is given 10C plus CSH is given C. It is 11C. Right. Continue that one. What about C3? C3 is nothing but C2 plus 2C. SH. C2 is 11C plus 2C. It is 13C. C4 is C3 plus 3C. It is N minus 1C. Cn minus 1 into N minus 1C. Sorry. Right. It is C3. It is 13C plus 3C. It is 16C. C5. It is C4 plus 4C. C4 is 16C plus 4C. It will be 20C. 20C is the answer. Like that you can carry. So if you remember the formula, everything is fine. Cn plus 1. Sorry. It is Cn. Cn. Cn is nothing but Cn minus 1 plus N minus 1 to CSH. Otherwise, Cn plus 1 is nothing but Cn plus N. Like that also. This is what I think I have done in the class. If you are calculating nth value, N minus 1. If you are calculating N plus 1 value, it will be N. Right? Both are correct. Both are correct. The nature of complex power supplied at the sending end of a transmission line. What is the nature of complex power at the sending end and receiving end both? It's a circle. Both at sending and receiving end. But at sending end, it will be in the first quadrant. At the receiving end, it will be in the third quadrant. They are asking in the sending end. It's a circle with center is in first quadrant. Center is in first quadrant. The nature of complex power at the sending end of a transmission line is a circle with center is in first quadrant. At the receiving end, it will be third quadrant. Circle only, but center is in third quadrant. Next question, students. A three-phase 50Hz synchronous generator is connected to an infinite bus. The maximum power that can be transferred to infinite bus is 1 per unit. P max is given 1 per unit. The mechanical input to the generator is √3/2 per unit. Right? So they have given that the value of PS is nothing but √3/2 per unit. The maximum power P max is given 1 per unit. The inertia constant H is given 5 seconds. Means 5 megajoules per MVA. So per MVA means you can take S as 1 MVA. S as 1 MVA. Find the natural frequency of oscillations. Natural frequency of oscillations. Right. So the frequency of the system is given 50 Hz. What is the natural frequency of oscillations? K is nothing but under root of 1 by m into dPe by d delta at delta is equivalent to delta naught. Right. At delta is equivalent to delta naught. Right. Where m is nothing but s into h divided by pi into f. S is 1, h is 5 divided by pi into 50. How much it will be? You can calculate this sum. 5 divided by pi into 5, 50 pi. We'll keep this one in terms of pi. No? So it is 1 by 10 pi. 1 by 10 pi. Otherwise, we'll keep like this one. But because options are in terms of pi only, no? It will be 5 by 50 pi. We'll keep like this. That is m value. And the mechanical power input is given root 3 by 2 per unit. Right? And maximum power is also given. What is the value of delta naught? Delta naught is nothing but sine inverse of Ps by P max 1. It is sine inverse of Ps is root 3 by 2. P max is given 1. Sine inverse of root 3 by 2 is 60 degrees. That is the value of delta naught. What is the dPe by d delta naught? dPe by d delta naught. And delta is equivalent to delta naught. It is nothing but P max 1 into cos delta. P max 1 is 1. Cos 60 it will be 1 by. It will be 1 by. Substitute that value here. Frequency of oscillations, it will be 1 by m. 1 by m is 50 pi divided by 5 into 1 by 2. So it is 50 pi divided by 10. It will be root 5 pi. Root 5 pi. Radians per second. Radians per second. Root 5 pi radians per second. Right, students, it is from steady state stability analysis by using the swing equation, right? So steady state stability analysis by using swing equation. There you can find the rotor frequency of oscillations. Rotor frequency of oscillations. One more question. There are some alternators connected in parallel, each with 20 MVA and 0.5 per unit reactance. The overall combination gives a short circuit capacity of 400 MVA. Then how many alternators are there in parallel? We know that MVA SC is nothing but MVA base divided by Z per unit. Right. They are given MVA SC is nothing but 400, which is MVA base. What is MVA base? 200 divided by Z per unit. Where Z per unit is nothing but 200 divided by 400. Divided by 400. How many it will be? 1 by 2 is 0.5. There are some alternates connected in parallel. So each alternator is having 200 MVA and 0.5. And the overall combination gives a short circuit capacity of 400 MVA. So this is Z per unit equivalent value. Equivalent value is giving it as 0.5. It is same as that of 1. Actually, it should be 1 only. Right? So if it is 4,000, 1 by 4,000. Actually, it is 4,000. So it is 4,000. If it is 4,000 students, how much it will come? 4,000. So it is 200 divided by 4,000. It is 0.05. Correct. For one alternate, it is 0.5. For how many alternates, it will be 0.05. For one alternate, it is 0.5. For how many alternates, it will be 0.05. Right. Suppose if two alternates are in parallel, it will be 0.5 divided by 2. Right. 0.5 divided by 2. So there are some alternates in parallel. Right. So what is Z per unit equivalent is equivalent to Z per unit actual value divided by n number of alternates in parallel. Right. So where n number of alternates is nothing but Z per unit initial value 0.5. The new value, what you got, Z per unit equivalent value is 0.05. How many it will be? 0.5 divided by 0.05. It will be 10. 10. There are 10 alternates in parallel. So typing mistake, students, just go through that one. So it is 4,000 MB. Right. So if it is 400, there is only one mission. Right. One more question from load flow analysis. A 100 bus power system network is consisting of 20 PV buses. In particular iteration of load flow problem solved by the Newton-Raphson load flow problem in polar coordinates, 10 of the load buses are having the voltage problem and converted into voltage control buses. Then the size of the Jacobian matrix will be. See, load buses are converted into PV buses. PQ buses are converted into PV buses. When PQ buses are converted into PV buses, the voltage will become known quantity. When voltage is becoming known, the size of Jacobian will reduce. Size of Jacobian will reduce. See, when PV bus is converted into PQ bus, then size of Jacobian will increase. When PQ bus is converted into PV bus, size of Jacobian will be reducing. Why? Because we are specifying the values of voltages. So here, some of the load buses are converted into voltage controlled buses. Voltage controlled buses are nothing but the PV buses. Therefore, size of the Jacobian will reduce. Not increase. Right, students? I will write here. When PV bus is converted into PQ bus. So for this one, Jacobian size increase. When PQ bus is converted into PV bus, Jacobian size reduces. Alright, students. So one more question. A 50 Hz 4-pole round rotor alternator rated for 100 MVA 11 kilovolts has an inertia constant of 1000 megajoules per MVA. If the mechanical input is suddenly raised to 1000 megawatts for an electrical load of 50 megawatt, then the rotor acceleration in mechanical degrees per second square. So underline this one, mechanical degrees. Right. The rotor acceleration alpha is nothing but 1 by m into the accelerating power PA, where accelerating power PA is nothing but mechanical input minus electrical power. where mechanical input is now 100, electrical output is 50. It is 100 minus 50. It will be 50 megawatt. 50 megawatt. And the value of M you have to calculate. M is nothing but S into H divided by pi into F. When you are writing pi here, it will be electrical radians, and in place of F, if you write N by 60, it will become mechanical radians. They are asking mechanical degrees. It will be S into H divided by 180 into, in place of F, it will be N by 60. The units are now megajoule second per mechanical degrees. Mechanical degrees. S is given. S is given, it is 100 MVA. H is given 10 megajoules per MVA divided by 180 into N per 4-pole mission. For 4-pole mission, what is the value of N? Is equivalent to, for 50H, it will be 1500 RPM. 1500 RPM. It is 1500 divided by 60. Substitute these values, students. How much is this one? 100 into 10 divided by 180. It is 0.22. 0.22. Now the angular acceleration alpha, it is 1 by 0.22 into 50 mega. It is 50 divided by 0.2. It is 227.27 mega. What is that one? Mechanical degree per second. Mechanical degree per second. Right? It is 225 nearly at it. Mechanical degree per second. Right. This is the most important part here. Right. Right, students. These are the some of the questions we have discussed within the specified time. Right, students. So those who are preparing very well, so cover almost all the areas of power system. Right, students. So every topic is important here. Every topic is important. And so this year, as the calculator is allowed, some numericals are expected. Not all numericals, some portion of the questions, right? We are expecting numerical, students. And students, so we have conducted already the online mega test, mega mock test for AEE students, and this is the QR to register for the examination. At any point of time, you can register for the examination and we can write the examination. Right, students? And we have launched new courses for APPSC IPO, Industrial Promotion Officer. There are subscriptions available for 3 months, 6 months and 12 months. And whereas the fee starts from 5,000 rupees for the old students. And this is the QR for the registration. Alright, students, all the best everybody.